Sometimes when you're dealing with equilibrium, they will give you the equilibrium constant, and you'll be asked to find one of the concentrations given. So, like the previous problems we were doing in the last video, you were able to get all of the equilibrium concentrations or pressures, and then you were able to find the equilibrium constant. Well, basically, this is just another variable. Sometimes they'll give you the equilibrium constant, and you have to find one of the variables. So, for example, here. In example 3, it says a sample of pure NO2 heated to 1,000 Kelvin decomposes, blah, 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 Kp equals 158. Analysis shows that the partial pressure of O2 is 0.25 atmospheres at equilibrium. Calculate the pressure of NO and NO2 at equilibrium. So again, we're going to start by making an ice table. And sometimes, you may think, well, do I need an ice table? Do I not? The more comfortable you become with this, the less you may or may not need an ice table. But it's always a good idea to use one. So the only thing that they tell us is they say a sample of pure NO2 gas is heated to 1,000 Kelvin. That's all that we know. So what does that tell us? So it tells us that we really don't know how much NO2 we started with, which you don't need to put the question mark in there. But what it really tells you is that you don't start with any NO or any O2. Okay, if you're starting with pure NO2, that means initially you don't have any of the NO or the O2. But then it does say analysis shows that the partial pressure of O2 is 0.25 at equilibrium. So O2 at equilibrium is 0.25, which means that it went up by 0.25 based on your initial and your equilibrium values. Okay, and if O2 went up by 0.25, then NO had to have gone up by, again, look at the stoichiometry. It's a 1-to-2 ratio. For every one of these, you get 2 of these. So NO had to have gone up by 0.5, which means the equilibrium value for NO is 0.50. So that's one of our questions. Calculate the pressure of NO at equilibrium. It's 0.5. Okay, now over here, again, if this went up by 0.5, this had to have gone down by 0.5, but that really doesn't matter because we don't know how much we started with. Okay, but we still need to find that value right there, so we're just going to call that X. So we know that our equilibrium equation is going to equal Kp equals the pressure of NO squared times the pressure of O2 over the pressure of NO2 also squared. Okay, and again, I just did that using the coefficients here from that balanced equation. So we have this number, we have this number, and we have this number. The only number we're missing is the pressure of NO2. So let's solve for the pressure of NO2. I'm going to move over here to the right. So the pressure of NO2 is going to equal, and remember that when you solve for a denominator, you basically just switch those two. So the pressure of NO2 goes over on the left, Kp goes on the bottom. So it's basically going to be the square root, because remember, it's squared, the square root of the pressure of NO squared times the pressure of O2 over Kp. Okay, so the pressure of NO2 is equal to the square root. The pressure of NO, we said, is 0.50 squared. Don't forget to square it. Pressure of O2 is 0.25. And Kp, it tells us, is 158. Sorry, that square root should come all the way down here. Okay, so now I'm going to go 0.50. I'm going to square it. I'm going to multiply by 0.25. I'm going to divide by 158. And then I'm going to take the square root of that answer. And I get a pressure of NO2 equal to 0.0199, or you could probably round up to 0.020. Okay, and that would be the pressure, and obviously that is atmospheres. They're not going to really care about that though. Okay, example 4. Calculate the equilibrium partial pressure of PCl3 in a 3-liter vessel that was charged with 0.123 atmospheres of PCl5. So again, let's start with our ice table. We're going to have PCl5 in equilibrium with PCl3 plus Cl2. This one gets a little bit more fun than the last one. Okay. So it says it was charged with 0.123 atmospheres of PCl5. So that means we're starting with 0.123 here, and that means we don't have any product to start with. And that's it. That's all that they tell us. Okay, and so that's where this one gets a little bit more difficult because we don't have an equilibrium number. And so we don't have an equilibrium number, so we're going to say, well, PCl5 is going to go down by a certain amount. We don't know how much, but it's going to go down by a certain amount. And usually when you don't know, you use a variable. So we're going to say it's going to go down by the value of x, which means that because it's a 1-to-1-to-1 ratio, that PCl3 is going to go up by x. And Cl2 is also going to go up by x. Now, obviously, if there were like a 2 here, then it would be 2x there. Okay, there's not a 2 there. Okay, there's just a 1 there, so it is just going up by x. Which means the equilibrium value is 0.123 minus x. PCl3 is x, and Cl2 is x. Okay, and so now let's set up our equilibrium problem. So we have 0.0121 is equal to PCl3 times Cl2, so x and x, that becomes x squared, over, and now we have 0.123 minus x. Okay, now at this point, to solve for x, there's a lot of work you got to do. You've got to take this right here, you've got to multiply it on both sides, and what you're going to end up with, guys, is you're going to end up with an equation where you're going to have to use the quadratic equation. Negative b plus or minus the square root of b squared minus 4ac over 2a, right? Okay, but on the AP exam, it's not a math test. It's a chemistry test. So they are never, ever going to make you use the quadratic equation. So what do you do? How do you make that easier on yourself? Is basically you assume that this x value is going to be a pretty small value. And so we're going to make an assumption here that 0.123 minus x is roughly equal to, notice my equal sign there, is because x is so small, it's going to be really just close to 0.123. And so that 0.123 value is not going to drop very much at all. Okay? So what does that mean? It means that when you get into a situation like this, where you have that x squared over a number minus x, 100% of the time, you can just take that x out of there. That minus x on the bottom, you just say, oh, x is going to be really small, and even on the answer key, they will even write, assume 0.123 minus x is roughly equal to, and they'll do the little equal sign, the little squiggly equal sign, is equal to 0.123. Okay? And you don't have to show that. You can just take that minus x out of there. And now the math gets way, way easier. We multiply this over here, so we're going to take 0.0121 times 0.123. We get a pretty small number. We take the square root of that number, and we get an x value equal to 0.0386. Okay, now what does that number tell us? It says calculate the equilibrium partial pressure of PCl3. Well, PCl3 is x, so it is 0.0386. And guess what? So is Cl2. It's also 0.0386. And if they asked us for the equilibrium pressure of PCl5, well, remember, that's 0.123 minus x. So we would have to take 0.123 minus 0.0386, and that would give us our value for PCl5. Okay, and the key there being, anytime you recognize a problem, and they will look just like this. You'll have an x squared on the top, and you'll have that minus x on the bottom. You can always take that minus x out, and that will result in a much, much easier math problem. And yes, your answer is going to be slightly off from the correct answer, but again, on the AP test, they've specifically said no quadratic equation. Okay, number 5. In a sealed, rigid, and previously evacuated container, a solid sample of NaN3 partially decomposes, creating a volume of 75 liters and an internal pressure of 1.2 atmospheres. The decomposition is represented by the equation below. Write the Kp expression for the reaction above. So Kp is going to equal, now again, be real careful because I see solid and I see solid here. Oh, well then Kp is just going to equal the concentration or pressure of the product. So that's the pressure of N2 cubed, and that's it. That's everything. Okay, you don't include the sodium solid, you don't include the sodium azide, the NaN3. Okay, you only include things that are gases in this case. Okay, and that's always the case. Anytime it's a solid, you never include solids in the equilibrium constant expression. Okay, and the internal pressure is 1.2 atmospheres. Well, what causes that 1.2 atmospheres is certainly the only thing that's in there is, the only gas that's in there is nitrogen. So if the internal pressure is 1.2 atmospheres, that means the pressure of nitrogen is 1.2. So to calculate the Kp value is just simply going to equal 1.2 cubed, which I believe is 1.728. Let's just check and make sure. Yes, it is. So with two significant figures, the answer is 1.7. And that's it on that one. That one's pretty straightforward. And yes, these are from pretty recent exams as well. This next one also. Okay, letter C looks just like this one. This one kind of goes back to what we learned a few days ago. So notice that we've got the same equation, NaN3, Na, and N2. NaN3, Na, and N2. But notice that all of the coefficients have now doubled. We went from 2, 2, 3 to 4, 4, 6. And we know that when that happens, what do we do with the equilibrium constant? We don't double it. We raise it to the power of that number. So we take our answer from before, the 1.7, and we square it. And 1.7 squared, I believe, is 2.89. Yes, 2.89, so we round that to 2.9. Okay, and again, that's your answer. That's all you've got to do. Okay, example number 6, and this is our last one. A student injects VB and O2 into a rigid container at a constant pressure of 400 Kelvin. The initial pressure of VB is 6. That of O2 is 4. VB react to produce VbO2. When the system reaches equilibrium, 2.5 atmospheres of VbO2 is present in the container. Determine the equilibrium partial pressures of VB and O2 in the container. Okay, so again, this one is one that where an ice table is certainly going to help. So VB plus O2 in equilibrium with VbO2, ICE. So what do they tell us? They tell us the initial pressure of VB is 6. Initial pressure of oxygen is 4. And again, what do they tell us without telling us is that the initial concentration or pressure of VbO2 is 0. Okay, if they don't say anything about the product, you can always assume that it's 0. Okay, and then it says when the system reaches equilibrium, 2.5 atmospheres of VbO2 is present. So that means that this is 2.5. Okay, determine the pressures of VbO2 in the container. So that means that VbO2 went up by 2.5. And notice the 1:1:1 ratio. That means that O2 went down by 2.5. And VB also goes down by 2.5. So this one becomes 1.5. And this one becomes 3.5. Okay, and so the pressure of VB equals 3.5. And the pressure of O2 equals 1.5. Okay. And that's all. Again, sometimes these are pretty straightforward. And again, this is from a pretty recent exam as well. So these are the types of questions you can expect. Part B, what is the value of equilibrium constant? Okay, well now we've got our equilibrium value. So now it's simply the Kp is going to equal the pressure of VbO2, 2.5 over 3.5. And they're all 1, so we don't need to square or cube anything, times 1.5 on the bottom. Okay, and again, check your math with mine. Do it along with me. Make sure that you're getting the same answer I am. So when I type this into my calculator, I go 2.5 divided by 3.5 divided by 1.5. Okay, and that equals 0.476. Okay? Now, these last couple, pretty straightforward, pretty easy ones. These are the ones here I really want you to pay attention to. Example 4, when you have that minus x on the bottom, that's when you've really got to make sure, okay, don't do, you can do the quadratic equation if you want. If you have a fancy calculator that can do the quadratic equation, by all means, if you know how to program that in and just do it on your calculator, and that's why they do that. That's why they say, hey, you know what? You can just take that minus x out of there, because some people aren't going to have the fancy calculators that can do the quadratic equation for you. Others will. So they say, just take that minus x out down here and don't use that, and that makes your math much, much easier.